Okay, so this video is kind of a continuation of the buffer discussion. In the last video, we did a couple examples of buffers where everything was acids and its conjugate bases. Let's do one where it's a base and its conjugate acid. So we want to know how to make a buffer with a pH of 10.5, which is obviously above 7, which makes it a base. And our compounds are CH3, CH2, 2, NH, and the same thing with an extra H in a Br. Because this has extra H's, this is probably going to be the acid in the story. And honestly, this first one has a Kb value, so we know it's the base. So figuring out which one's the acid, which one's the base is kind of how these things start. So what we have is, because this is a base, we need to do POH equals pKb plus the log of the concentration of conjugate acid divided by the concentration of weak base. Okay? Well, we don't have all of those things, but we can figure it out. Okay? So, to get POH, we're going to have to take pH minus 14. Okay? So, that's going to be 3.5. To get pKb, we're going to have to do the negative log of Kb, which is 6.9 times 10 to the negative 4th. And I don't know what the answer is, but we'll figure it out. Negative log of 6.9 e to the minus 4th. I got 3.16. Okay. I'll wait to round until the end, but technically we only get 2 sig figs out of that. Okay. And then we have to know our concentration of conjugate acid and conjugate base. We're going to know one of the two. We need to figure out which one we know. So if this thing has a Kb value, this would mean this is the base, which means this is our conjugate acid. Which means we know this value, so the conjugate acid is 0.200. And this is the one we don't know. So I'm going to show all my work, and let's see what happens. All right, so I'm going to rewrite everything. POH was 3.5, pKb is 3.16, plus the log of conjugate acid was 0.200, and weak base is what we don't know. Okay, so now we need to do some algebra. So we subtract the 3.16 off of both sides. Don't trust my math all of a sudden, but I get 0.34, sorry. 0.34 over here. Okay, so that cancels out, and that is equal to the log of 0.2 divided by x. We need to get rid of the log now. So to get rid of logarithms, this is log base 10, so we do 10 to the whatever on both sides. And so 10 to the 0.34 is equal to 0.200 divided by x. We need to solve for x. So what I'm going to do is I'm going to multiply x on both sides to get it out of the bottom. And then we need to solve for x by itself. So on this side, so over here it'll cancel out, but over here we have this 10 to the 0.34. We're going to divide that on both sides. So when I rewrite this, x equals 0.200 divided by 10 to the 0.34. Okay. I just made all this problem up, so let's plug everything in. So 0.200 divided by, I'm going to put it in parentheses, 10 to the 0.34. Okay. Right. And I got an answer of 0.091. Oh, sorry, 0.091. So what this means is if we made a buffer that had 0.2 molar of the conjugate acid and 0.091 molar of the base, our final pH would be 10.5. okay? So, other than having to solve for POH before doing the rest of this problem, it's pretty similar to what we saw in the last couple problems. Not a drastic difference here, okay? So, let's kind of continue just broader discussions about buffers, and then we'll switch topics, I guess. So, we need to talk about the limitations of buffers. So, as I kind of stated at the beginning of the last video, essentially a buffer is made from a weak acid and its conjugate base, or a weak base and its conjugate acid, as we just saw in the last example. And it's designed to resist pH changes, but it can only do so for so long. You can't, like, you know, have a 0.1 molar of weak acid and a 0.1 molar of of conjugate base and expect it to tolerate, like, you know, 50 molar of acid or 50 molar of base. So typically, it kind of depends on the buffer itself, but the general idea here is for anything to be an effective buffer, you need the ratio of weak acid and conjugate base, or weak base and conjugate acid, to be within a factor of 10 of each other. So what that means is you need the ratio of conjugate base to weak acid, that ratio to be somewhere between 0.10 and 10. If it gets too far out of that range, you don't have a good balance of acid and base, and it'll tolerate either the addition of, if you have too much acid, it'll tolerate the addition of base, but not tolerate the addition of acid. So you have to have both, okay? The other consequence of this is that your pH is only effective plus or minus 1 pH unit of your pKa value. So plus or minus 1 pH unit of whatever the pKa is, or I guess pKb. Okay, so what that means is if you're trying to design a buffer and it has a certain concentration, like for this example, we wanted something that's 10.5, well that worked out really nicely because the POH was 3.5, the pKb was between 2.5 and 4.5. It was actually pretty close, 3.16. If we had wanted a POH of like 4.5, we would need to pick new molecules, something with a pKb closer to 4.5. Okay, you can't just keep dumping in a huge amount of acid compared to base or base compared to acid to make it get to the pH you want or POH you want. These have to be pretty similar, which means there's going to be a limit of plus or minus 1 unit between these two. If this gets too far away from this, it's not going to work. It's not going to function as a buffer. Okay. This also introduces the idea of something called buffer capacity. Basically, it's a measure of how much acid and base can this thing withstand. It turns out that it's really simple. The higher the concentration of weak acid and conjugate base, the more acid and base it can withstand. So the higher the concentration of weak acid and conjugate base, or the base equivalent of these things, so if you had the weak base and the conjugate acid, the more acid and base it can withstand. It can withstand. So, if we wanted to make, well, actually let's pick one of the ones from the previous video. So let's say we wanted a pH where the pKa, or the pH is equal to the pKa. So, in other words, the acid and the base, the weak acid and its conjugate base have to be the same. If you made this 0.01 molar and 0.01 molar, this would still be equal. They would cancel out, and you'd get pH equals to pKa. But it wouldn't be able to withstand very much acid and base. If you made this 10 molar and 10 molar, that's going to withstand a whole lot more acid and base. So just because you've got the right pH and pKa value doesn't mean that your buffer is going to be very good. What matters is how high these values are and making sure they're in the right ratio. So like for this example, we said that to make a buffer with a pH of 5 using acetic acid and sodium acetate, we needed this to be in a 0.725 to 1.32 ratio. Okay, the 1.32 is the number on top. Well, if we doubled both of those numbers, the ratio would be the same, so we'd still get a pH of 5, but it would be twice as good of a buffer because you have more acid and base to withstand things. Okay, so it's not a huge deal at the moment, but it's kind of one of those things that if you ever get out in the real world and you're making a buffer for a lab or something, understanding these three concepts is kind of important. Okay. And then I briefly want to mention the idea of another way to make buffers. We are not going to do much with this, but I want to at least mention it. So another option for buffers. Okay, well, since we've done the acetic acid one a few times, we've got a pretty good handle on how that one works. If you started with only the weak acid, you know, we end up with this solution. If you started with double the concentration, suppose we wanted this to be 1 molar and this to be 1 molar. If we started with 2 molar of this, and we just titrated it with a strong base, as the base reacts, it's going to pull off the H+ and form this. What you can literally do is just titrate this with a strong base. So suppose we were trying to get that 4.74 buffer again, just titrate it until you get a pH of 4.74. Because what that means is that all of the strong base has been neutralized up to that point, but it has been converting to weak base, the conjugate base of this. So if you titrate this until it's 4.74, what means is half of this has been titrated, and so you'll have 1 molar of this, and the other mole will be converted to this. It's a little complicated, but technically, you'll have a buffer. With the concentration of CH3COOH equal to the concentration of CH3COO minus, and they'll both be equal to 1 molar. Because you started with 2, you titrated half of it. You converted half of it to the conjugate base by titrating it. A little weird, but the consequences of that will be important later when we talk about titrations. Like if you try to titrate a weak acid, you end up forming a buffer along the way, which can kind of mess up your interpretation of your titration results. It actually makes things a little complicated, but that's okay. So, all right, thank you.